Hello everyone and welcome back to another video. Today we're going to start going over chapter 2 of the textbook, which is all about prime numbers. And in this particular video, we'll prove some facts about prime numbers and use them to ultimately prove the fundamental theorem of arithmetic, which, as the name suggests, is a very important theorem about the natural numbers. So to begin with, let's start by talking about the prime numbers, or introducing the concept of a prime number. So the study of prime numbers is one of the main focuses of number theory. People have been studying prime numbers for thousands of years, and there are still unanswered questions. In this course, we're going to focus on more elementary questions about primes, but investigations of unanswered questions about prime numbers have yielded and will continue to yield some of the most beautiful mathematical proofs and most beautiful mathematical results in the history of math. So let's start at the very beginning with a definition of prime numbers. So to define them, a natural number p greater than 1 is prime if and only if, so I'll just use IFF for if and only if, p is not the product of natural numbers less than p. In other words, p is prime if it has exactly two divisors, one in itself. So it cannot be the product of natural numbers that are less than it. It can only be the product of p and 1, of 1 and p. So let's look at some examples of these. Just like the first few prime numbers. 2, because the only way to get to 2 is 1 and 2. And then we also have 3, which is the product of 1 and 3. Those are the only factors of 3. 5 is a product of 1 and 5. 7 is a product of 1 and 7. And then we also know the 11 is a product of 1 and 11, and then this list goes on and on and on. It's actually an infinite list of numbers, which we're going to prove in a later video. Alternatively, let's look at the definition of a composite number. Which can kind of be thought of as like the opposite of a prime number. So for a composite number, a natural number n is composite if and only if n is a product of natural numbers less than n. So you can kind of view this as the opposite of a prime number. However, 1 is the only natural number that doesn't fit into either of these categories. So, similarly, for some examples of this, let's look at, for example, 4 is 2 times 2. 2 and 2 are both less than 4, so it's a product of natural numbers, is a product of natural numbers less than n. Sorry, I didn't finish the definition. Sorry about that. Okay, so 4 is the product of 2 and 2, so it's the product of natural numbers that are less than 4. Similarly, 6 is the product of 3 and 2. So it's the product of natural numbers two natural numbers, 3 and 2, that are less than n, that are less than 6. Similarly, you have 8, which is 4 times 2, but not all these are multiples of 2. So 9, for example, is another one where it's 3 times 3. So it's the product of natural numbers that are less than it. So yeah, all of these would be composite, and this list also continues on forever. One thing that you might notice right away is that the only even number that is prime is 2. This is because all the other even numbers, by definition, are products of 2 and another number. It's a product of 2 and another number that is also less than that even number. The only exception is 2, because the multiple of 2 that 2 is 2 times 1, and 2 times 1, like 2 is not less than that number. It's only 1 in itself. So when a number is only the product of 1 and itself, then it's a prime number. The only exception to this is 1, because 1 is itself, so it needs to have 2 factors to be considered a prime number. So yeah, with these definitions kind of understood, let's go into, and hopefully you should remember a lot of these from like very early on in your education. But the more interesting part here is what we're going to start proving about them using these more rigorous definitions. So let's start proving some theorems about prime numbers. So the first one that we're going to prove is theorem 2.1 in the textbook. And this theorem is, if n is a natural number greater than 1, then there exists a prime p such that p divides n. Okay, so this is saying for every number larger than 1, there is a prime number that exists that divides it. And now this will be the first example of this, but we're going to see a lot of examples of this throughout this video. We're going to use strong induction. So if you don't remember what a proof by induction is, I'd recommend you go back to my series on Introduction to Proof, rewatch that video. But I think also this video is going to give you a much stronger, like, practical use case of strong induction. Because these proofs can be a little complicated if you're not familiar with them, feel a little bit weird compared to other proofs, but ultimately you'll see how useful they can be in proving things about primes for all the natural numbers. So let's start with our proof. So we're going to let Sn be the statement that there exists a prime p such that p divides n, where n is a natural number. And what we want to do is prove that Sn is true for every single natural number above 1. So where n is greater than 1 strictly, we want to prove that Sn is true. And then once we do that, we've proven the theorem to be correct. So we're going to start with the base case, where n equals 2. If n equals 2, then Sn is true since 2 is prime and 2 divides 2. So just for this first case where n is 2, we have that 2 is a prime. 2 divides 2, so S2 or Sn when n is 2 is true. So next, let's prove the inductive step. So we have this first rung. Now let's prove that we can do this, or once we have this initial step, we can continue proving this for the rest of the natural numbers. So what we're going to do is let k be an integer where k is greater than or equal to 2, and assume Sm is true for each integer m where 2 is less than or equal to m is less than or equal to k. So what we're assuming here is we're assuming that S of m is true. So for all of these integers between 2 and k, we can find some prime that divides each of those integers. So that's what we're assuming to be the case here. The reason why this works is because when k is 2, we're starting with just the fact that we're starting with, and what we're trying to show is that S of k plus 1 is true once we assume this. So the reasons why this works is because we start with just k equals 2, and then show that knowing S of 2 is true proves that S of 3 is true. Okay, and now we know S of 2 and S of 3 is true. Well, now using those two together, we can prove that S of 4 is true. Now we have those three things are true. And then using those, we can prove S of 5 is true. So we keep doing this step, and by doing this in this generalized format here in the inductive step, and proving that Sk plus 1 is true, then we can prove that entire chain. So we're going to use this sort of chain of logic for a lot of these proofs that we're using throughout this video. And this is what's called strong induction, or proof by strong induction. So let's start with the fact, since k plus 1 is greater than 1, k plus 1 is either prime or composite. And what we're going to do here is split this situation into cases. So case 1. Assume, and what we're going to show is that whether k plus 1 is prime or composite, Sk plus 1 is true. Then assume k plus 1 is prime, then Sk plus 1 is true since k plus 1 is prime and k plus 1 divides k plus 1, obviously, because k plus 1 times 1 equals k plus 1. Okay, so now for case 2, let's assume that k plus 1 is composite. Now here we know k plus 1 is composite, so that means there's two numbers below k plus 1 that multiply together and give you k plus 1. So let's write this out more formally. Then k plus 1 equals AB, where A and B are naturals, and 1 is less than A, B is less than k plus 1, i.e. 2 is less than or equal to AB is less than or equal to k. And why this is helpful, if you look at this inequality down here and compare it to this inequality up here, you see that they are very similar. And this is what we're going to ultimately use to prove this to be the case. So we know that k plus 1 equals a times b, where a and b are between 2 and k. So since a, or 2 less than or equal to a less than or equal to k, SA is true. Remember, because that was part of our assumption. So a equals px, so there's some prime, which we'll call p, so a equals px, or some prime that divides a, which we'll call p, for some px that are naturals, where p is prime. Okay. And this means, hence, k plus 1 equals ab, but that means that it equals pxb. So p divides k plus 1. Therefore, based on that, or thus, k plus 1 is true. So regardless of whether k plus 1 is prime or composite, all of these other facts about so like sk and sk, or s2 and s3 and da 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 all the way to sk, regardless of whether k plus 1 is composite or prime, though that list of statements being true implies that k plus 1 is true. So let's write that out more formally. And this means Sn is true for all integers n where n is greater than 1. And that is what we were trying to prove. So what we've shown here is that every single integer greater than 1 is divisible by at least one prime number. Do I have space for another proof? Not quite. Okay. Well, I have some space. Let's close this one off. And then close this part off here. Trying to think of the best way to do this. I think we could start here and then kind of like run up to the start there. Let's do it like that. Okay, so for this one, so this next theorem, we're going to, this is theorem 2.3, which we're also going to prove about the primes. So we're going to prove here that a natural number n greater than 1 is prime if and only if for all primes p less than or equal to square root of n, p does not divide n. So actually what this theorem does is give us our first way of testing whether a number is prime or not. So what we can do basically, it's saying, is if we have a number n, we can test if that number is prime by checking every single prime below the square root of n and see if those numbers divide n. And if none of them do, then p is prime. So let's do this proof. So what we see here, this is a biconditional statement. So to prove it, we're going to have to prove each direction of the biconditional. Now the first direction is going to be a little bit quicker, so we can start there. So for this one, we're just going to suppose n is a natural such that n is prime and n is greater than 1. Then, by the definition of a prime number, one and n are the only numbers that divide n. So since 1 is not prime and n is greater than or equal to the square root of n, because the only way that n could be, or I guess either way, n is a natural, so it's greater than or equal to 1, and so n is greater than or equal to the square root of n. But even just by the fact that n is greater than 1, you can see that. And n is greater than or equal to square root of n. Or wait, I think I just need to say greater than. Yes. So just by the fact that n is greater than 1, n is greater than square root of n, all primes p less than or equal to square root of n do not divide n. So that means if n is prime, none of the primes below the square root of n divide n. So next what we're going to do is go over, actually I'll just scroll up and then we can go from there. We can prove the other direction of the biconditional statement. The other direction of this biconditional statement looks like this. So for this one, we're going to use the contrapositive approach. So if you remember, the contrapositive approach starts by assuming that the result is not true, and then proving that the starting point is not true from there. So it's basically showing by showing that if we show that if a natural number n greater than 1 is not prime, that means that for all primes n greater than or equal to n, p does divide n for at least one prime, because negation of for all is at least one. Then that basically shows the opposite direction. For all primes p less than or equal to n, p does not divide n. Then then the natural number n is prime. So what we're doing here is using the contrapositive approach, where this side is q, this side is p. We're showing p implies, or q implies p, by showing not p implies not q. And if you want more direction on the contrapositive approach, I would recommend watching my intro to proof video once again, because I explained it a little bit more in depth in that particular video. So what we're going to do here is start by supposing that n such that n is composite and n is greater than 1. Okay, so n is a natural number such that n is composite and n is greater than 1. Then n equals ab for some a, b that are naturals where a and b is greater than 1. Suppose, for the sake of contradiction, that both a and b, or we'll say, yeah, we'll write it like this, that both a and b are greater than the square root of n. Then ab is greater than square root of n times square root of n, which equals n. So ab is greater than n. However, ab equals n, so we have a contradiction. This means that at least one of a and b is less than the square root of n, or less than or equal to the square root of n. Hence, one of a or b must be less than or equal to n, or sorry, less than or equal to square root of n. So we're gonna, without loss of generality, one of these must be less than or equal to n. So we're just going to say that a is less than or equal to n. You could do the same logic if it was the case with b, so we're just doing it without loss of generality here. A is less than or equal to the square root of n. By theorem 2.1, there exists some prime p. So we're calling back to the theorem from before. P that divides a. So P equals, or sorry, so A equals px for some x. Now, since P divides A, P is less than or equal to A, which is less than or equal to the square root of n. Thus, n equals AB, which equals PXB. So, P divides n. Therefore, based on that, we have found that there exists some P if n is composite. We found that there exists at least some P that divides n. So what that shows us is that basically, if there is a composite number n, then there exists some P that such that P divides n. Now, by contrapositive proof, what that shows us is that for all primes, if for all primes P less than or equal to square root of n, P does not divide n, then that natural number n greater than 1 is prime. So what it's done is shown us that opposite direction through a contrapositive proof. So we can just write that last sentence out just to make it explicit. So let's look at some examples of this. So just to see how this can show us that a certain number is prime, we're going to show that 101 is prime. Or sorry. So the first thing that we want to do is see what the square root of 101 is. Now what we know is the square root of 101 is between 10 and 11, because 10 squared is 100 and 11 squared is 121. 101 is between that, so the square root also must be between that. So what we need to show is that every prime less than 10, less than or equal to 10, does not divide 101. So the primes that are less than 10 are 2, 3, 5, and 7, and we'll just check them off when we know that they don't divide 101. So let's look at 2. For multiples of 2, we got 2, 4, continue all the way to 100, 102, and that shows that 101, 2 does not divide 101, so we can cross that one out. For 3, we can do a similar thing. 3, 6, 99, 102. So 3 does not divide 101. For 5, we have 5, 10, 15, 20, all the way up to 100, 105. So that 5 does not divide 101. 7. We have 7, 14, all the way to 98, 105, So 7 does not divide 101. So by theorem 2.3, 11 is, 101 is, 11 too. But 101 is prime. That's what we show. That's what we've shown here. Wow, okay. Okay, so with that, those are the two theorems that we're going to start with for this section, to just thinking about discussing prime numbers. These are the two theorems that the textbook shows just to kind of introduce prime numbers, how they work. And now, with that, we can actually get into the Fundamental Theorem of Arithmetic, which is the title of this video and what we're going to prove next. So, this next section is about the Fundamental Theorem of Arithmetic. So this theorem is a very important theorem about natural numbers. It essentially is going to show us that there is this unique code of prime numbers that we can put together, put them in order, and have them uniquely correspond to one integer. And every single natural number has this code of prime numbers. It's unique for each of these numbers, and that's what we're trying to prove in the Fundamental Theorem of Arithmetic. And there's going to be two parts to the theorem, uniqueness or existence and uniqueness, and those are what we're going to show in the rest of this video. So let's just write out what the Fundamental Theorem of Arithmetic even is. So the Fundamental Theorem of Arithmetic is that every natural number greater than 1 is either a prime number or it can be expressed as a finite product of prime numbers where the expression is unique up to the order of the factors. And that is the fundamental theorem of arithmetic. And we're going to prove this in two parts. The first thing that we're going to do is prove the existence of this prime factorization, is what it's called. And then what we're going to do is go on to prove a lemma, and then that lemma is going to help us prove the uniqueness of this expression. So basically all it's showing is that every natural number has this unique factorization of prime numbers. First, we're going to show that one exists, then we're going to prove that it is unique to that number. So yeah, let's begin. So the first thing that we're going to do is start with theorem 2.7, which is existence. And this theorem basically explains, so some of these theorems are going to be written out pretty long, but hopefully you can understand the gist from the original statement. So every natural number greater than 1 is either a prime number or it can be expressed as a finite product of prime numbers. That is, okay, so the textbook restates the theorem a couple of times. For brevity, I'm just going to leave it at this. The way it kind of explains it, we're going to see later on. But I'll explain it in the statement of the inductive step a little bit. So for proof, let Sn, so this is going to write this out a little bit more formally, be the statement that n equals p1 r1 p2 r2 dot 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 pm rm for distinct primes P1, P2, PM, and natural numbers. R1, R2, dot, 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 RM. So basically all it's saying is we have this factorization of prime numbers So P1 could be just one prime number. That's the amount of times that P1 appears. R1 would be the amount of times that P1 appears within the factorization. P2 is another prime number. R2 is the amount of times that P2 appears in the factorization. That continues for m different prime numbers. And what this is saying is that n is just expressed as a product of entirely prime numbers where there's no composites in there. And we can do that for every single n. And that is equivalent to this statement up here. So if we can prove that that's true for every n greater than 1, then we've shown that we've basically demonstrated the existence of the fundamental theorem of arithmetic. So let's start with the base case. So S of 2 is true because 2 equals 2 to the power of 1 and 2 is prime. Simple. So for 2, we just have the simple prime factorization that 2 is 2 to the power of 1. So for prime numbers, this is very simple, writing out their prime factorization. It's already in the form of a prime factorization. So for the inductive step, we're going to also, once again, use strong induction. So we're going to let k be a natural number where k is greater than or equal to 2, and assume Sx is true for all x naturals where 2 is less than or equal to x, less than or equal to k. Okay, so for the next step, then we're going to proceed similar to before. K plus 1 is either prime or composite. So case 1, if k plus 1 is prime, k plus 1 equals p for some prime p. P equals k plus 1. Because k plus 1 is prime. Hence, S k plus 1 is true. Yeah, we'll just, let's just start this line. And then the second case that we're going to go over is suppose k plus 1 is composite. So AB equals k plus 1 for some A, B that are naturals, where 1 is less than A, B is less than k plus 1. Hence, SA is true and SB is true. Because remember, that was the inductive hypothesis, was that everything between 2 and k must be true. A and B are both between 2 and k, so this statement is true for each of those letters. So this means that we have a prime factorization for A, which we'll express like this, where this pi symbol is just referring to like a product notation. And B equals pi R J equals 1. Very similar like a for loop in coding. Where Pi Q J are primes and Mi N J are naturals. So it's just showing that A and B are both have prime factorizations because SA is true, SB is true. So what we're going to do is multiply these prime factorizations together, and this is going to show us that thus K plus 1 equals AB, which means that it equals this product. So, since these are both products of primes, their product is a product of two products of primes. It's all a product of primes. So, S K plus 1 is true. Hence, S2 and SK implies SK plus 1. So what we've done here is proven the existence of the prime factorization in the fundamental theorem of arithmetic. So this shows basically that every single natural number has a prime factorization. Now the next question we want to ask, is that prime factorization unique? Do some numbers have two different prime factorizations? Or is this prime factorization completely unique? And that's what we're going to prove next. Now, the first step that we need in order to prove this is a lemma. A lemma is just a theorem that's used to prove another theorem, essentially. So in this case, the lemma that we're going to go over in this situation is lemma 2.8, and in the textbook this is let P and Q1, Q2, Qn all be primes, and let K be a natural number such that pk equals q1, q2, ... qn. So basically what we're saying here is that we're defining p and then these sets of primes such that p divides the product of all these q's. Then P equals Qi for some I. So basically all this is saying is if a prime number is equal to, if there's a prime number that divides the product of a bunch of primes, then that prime number initially must be equal to one of those primes. So let's prove that here. And once again, we're also going to use strong induction. So let P be a prime. And then we're going to let Sn be the statement let Sn be the statement that if P divides Q1, Q2, Qn. So notice n is this thing that we're indexing on. It's the number of different primes that are being divided by. We're showing that if P divides 1 prime, and then 2 primes, and then 3 primes. So we're showing that it equals one of those primes in each of these cases, all the way as n approaches infinity. So, yeah. That if P divides Q1, Q2, Qn, where Q1, Q2, Qn are primes, then P equals Qi for some I. So let's see kind of how this works with the base case. We'll start there. S1 is true because, here, let's actually write it like this, shorthand. Because if P divides Q1, where P, Q1 are both prime, then P equals Q1. So you note here that n is equal to 1. So this product of primes is just Q1. If n was 2, it'd be Q1, Q2. If n was 3, it'd be Q1, Q2, Q3. But here, since n is 1, that's what we're starting with. It's just Q1. So we have to show that P equals Q1. So P equals Q1 here because 1 and Q1 are the only divisor of Q1, and P does not equal 1. So what we've shown here, P must be one of these divisors of Q1. It's not 1, so and the only other option is Q1, so P must be equal to Q1. So next, let's go and look at the inductive step. So here we're going to let K be a natural where K is greater than or equal to 1, and assume SM is true for all M that are integer or natural numbers, where 1 is less than or equal to M is less than or equal to K. And then suppose P divides Q1, Q2, or not comma, sorry, dot 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 Qm, or sorry, it needs to be K plus 1. Q K plus 1, because we're trying to show that it equals to one of the Q's in that set of Q to K plus 1, where P, Q1, Q2, Q, K plus 1 are primes. So either P divides Q, Q1, Q2, dot 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 qk, or it doesn't. So it's saying that either p divides everything except this last k plus 1, or it doesn't. Or p does not divide q1, q2, qk. It either does or it doesn't. So case 1, we're going to assume p divides q1, q2, qk. Since S of k is true, p equals qi for some I. So S k plus 1 must be true. Since qi is in the set of these q's from before. The only thing that wouldn't be included is k plus 1, but qi is one of these that come before k plus 1. So it's in this set. Now case 2, suppose p does not divide q1, q2, qk. Then the GCD of p and q1, q2, qk equals 1. And the reason why this is the only factors of p are q and 1. And since p does not divide this product of primes, p cannot be a common divisor. So the only common divisor they have would be 1. So the greatest common divisor is 1. Okay, so now we're going to remember from before, we know that p divides this full set here. So we know that PC, okay, wait, let's write it like this. We know that PC equals q1, q2, qk plus 1 for some c. Okay, and this is like the natural number. For some c, that's a natural. So by theorem 1.39, which if you remember from before is that one where it's if the GCD is 1, then 1 is one of the things is the linear is a linear combination of one of them and the other one. So we'll just write it out. Where 1 equals px plus q1 q2 qk times y because remember the GCD of these two is equal to 1. So what we know, qk plus 1 equals qk plus 1 times 1, which equals qk plus 1 times px plus q1 q2 qk y, which equals pqk plus 1 x. And notice here that if we factor in that k plus 1 here, it's going to give you that full sum again. So what we have is plus q1, q2, dot, 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 q, k plus 1, y. And then this will equal pq, k plus 1, x, plus pc, y. Because remember, pc equals this full product because p divides this full product. And then we can factor out the p, and that gives us p, q, k plus 1, x plus c, y. Okay, so now we can move on. And what this shows us is that thus p divides q, k plus 1, and since S1 is true, so if p is equal to or divides a single prime number or a product of just one prime, p equals q, k plus 1. So S, k plus 1 is true. So what we've shown is that if it doesn't divide this whole product apart from this k plus 1, then it must equal that k plus 1. And then this means thus that hence S1 and dot 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 sk imply sk plus 1. So Sn is true for all n greater than or equal to 1. So what we've just shown here, crucially, is that if we have a product of primes and we know that one prime divides that product of primes, then what we know is that this prime that divides the product of primes equals one of the primes within that product. That's what this lemma shows. And this is going to be extremely helpful in our uniqueness proof. Now, the textbook gives the uniqueness theorem in many different ways, similar to the existence theorem from before that we see. Actually, we'll just write this, go this all the way down. Or we'll write it like this, and then maybe we'll have space at the bottom for something else later. Okay, but ooh, we need a little more space here too. Always need some space. Okay. So this last thing that we're going to prove is the uniqueness of the fundamental theorem of arithmetic. So theorem 2.9, and that's uniqueness. Okay, so the way that they write it out in this in the textbook is very long. They write it in multiple different ways, but what I'll do is I'll express this in the simplest form here. So if we express the same natural number as the product of powers of distinct primes, then the expressions are identical, except or except for the ordering of the factors. Of factors. Okay. So for our proof, what we're going to do, assume. So what this is basically saying is that if we have this one natural number and we have a product of powers of distinct primes, which we know we can produce, and we have two of these, then all of these expressions are identical. There can't be two distinct product of powers of primes that correspond to the same natural number. Those two products of powers of primes must be identical. So what we're going to assume, we're going to do, for this proof, we're going to show a proof by contradiction. So suppose for contradiction that there exists some natural number with multiple distinct prime factorizations. And what we're going to do is let S be the set of all of these such numbers. The set of all natural numbers with distinct prime factorizations. Okay. So by the well-ordering axiom, or by the well-ordering principle, and if you remember this from before, that's basically saying if we have a set of natural numbers, we can pick one that's the lowest. There must be one that's the lowest. So by the well-ordering axiom, S has some smallest element. Let N be the smallest element of S. Thus what we have is two distinct prime factorizations of the smallest element n. So thus n equals p1, p2, pk equals q1, q2, ql, where p1, p2, pk and q1, q2, ql are distinct. Oh my gosh, it cannot keep up with me. Distinct, unordered lists of primes. So next what we're going to do is we're going to let P2 P3 pk equals C. So P1 C equals Q1 Q2 QL. And if you remember this looks very similar to our expression of lemma 2.8 from earlier. If you remember from before, So if we have pk equal to this product of primes, then p equals qi for one of them. So we have that p1 times c equals this product of primes. So p1 divides this product of primes, and p1 is a prime. So by lemma 2.8, p1 equals qi for some I that's a natural, where 1 is less than or equal to I is less than or equal to L. Without loss of generality, because it's going to be for one of these i's, and the order of these q's doesn't actually matter. So without loss of generality, p1 equals q1. So since p1 does not equal 0, 0 is not a prime, p2, p3, pk equals q2, q3, ql. Now, one thing to note is since p1 equals q1, this means that since these were distinct, these lists were distinct and p1 equals q1, q2 through ql must be distinct from p2, pk. So note that p2, p3, pk and q2, q3, ql must be distinct. So since p1 c equals n and p is greater than 1, c has to be less than n. However, c equals p2, p3, pk. Remember from how we defined it before. So that also means that it equals q2, q3, ql. So C has two distinct prime factorizations. So C is contained by S, because S is just the set of all natural numbers with two distinct prime factorizations, or at least two distinct prime factorizations. Since n is the smallest element, this means that n has to be less than or equal to c. But c must be less than n. Hence, we have a contradiction. And now remember what we supposed for the sake of contradiction. We supposed that there exists some natural number with multiple distinct prime factorizations. But that leads us to a contradiction. Therefore, all natural numbers have unique prime factorizations. And that is it. That is our proof of uniqueness. So what we've just shown here is that if two numbers, so we know that every number has a distinct prime factorization, or has some prime factorization. Now what we've just shown here is that there's only one possible prime factorization for each of these numbers. If we find two, they must be identical, apart from just the ordering of the factors. So this kind of shows that there is this sort of unique code, or of this unique product of primes that corresponds to each natural number. And this is a very useful result because it provides us with a fundamental understanding of the structure of natural numbers. We see what elements they ultimately reduce down to, which are the primes. Now, for an example of this, let's just look very quickly at a very brief example. Let's look at the natural number 12, for example. 12. Well, 12, its prime factorization is 2 squared, which is 4 times 3. 4 times 3, 12. This is a unique factorization. This is like a unique code that corresponds exactly to 12. This is the base components that 12 is made up of. 2 2's and a 3. Multiply them together, 12. 240, much larger number. But for this one, it's 2 to the 4 times 3 times 5. And all of these are primes. And you can do this for every single natural number in all of existence. So what we know now, based on all of this, is that there is a list that every single number is made out of. And this shows us what ultimately at baseline these natural numbers are made up of. They're made up of primes. They're products of primes. And this gives us a very good insight into just the structure of what a natural number is, which is ultimately what we study in number theory. That's kind of the whole point, is to understand the structure of the natural numbers, to understand how they work, to understand how they operate, and to get ultimately some understanding of how these natural numbers work. Oh wow, so I zoomed out a lot there, but this is basically what we did today. We showed a few facts about prime numbers, defined prime numbers, and then discussed the fundamental theorem of arithmetic, and then proved the existence and the uniqueness of the prime factorizations for every natural number. So that is ultimately what we've done today. But that is everything that I have for this video. I went a little long today, but I think it's okay. This was a bigger topic. Hopefully you enjoyed. And yeah, if you join me next time, next video, we're going to discuss some of the applications of the fundamental theorem of arithmetic. We're going to see what sort of theorems we can prove using this fundamental theorem. But without further ado, thank you all for watching. If you enjoyed the video, please like. If you want to see more content, keep getting notifications about this number theory series. Please subscribe if you really enjoy it and want to support. I have a Patreon link down below. Additionally, I have a Discord if you want to go in and ask questions or discuss. But yeah, that's all that I have for this video. Thank you all for watching, and I hope to see you all in the next video. Peace.